All right, welcome back. We're going to do part 2 now of section 3.1. So we're starting back with number 12. And this page is a lot about making sure that you understand function notation and exactly what it is that you're being asked when you see these kinds of notations on your homework. So number 12 is giving you a graph this time and asking you to find some function values for the first 4 parts. Okay, function f is on the graph, so it's just what looks like part of a quadratic or a parabola, if you remember that name, and then another piece of another graph. So this is just a given graph drawn. There's no real equation for this function, but we can still find function values. Okay. So remember the notation when you're finding f of 2. I'm going to write up here to, let's just remember that, when you're given function notation, whatever's in the parentheses is x, and what you're looking for over here is y. So in part A, if it's asking me for f of 2, then I'm going to go to an ordered pair on the graph where the x value is 2. So if I look at that, that would be this point right here. Okay? And if you wrote that ordered pair down, I'll just write it underneath here, but that would be the point 2, 0, right? X is 2, y is 0 of that point. So if you're asked to find f of 2, then that's asking you to find the y value when x is 2, so that would be 0. Okay? All right, so we're going to do the same thing with f of 1. So if I go to 1 on the graph and find the point that's actually on the graph, that would be right there. And that would be the ordered pair 1, 3, right? Just an ordered pair. So again, this notation is just asking you what's the y value when x is 1, so that would be 3. All right, 0, f of 0, it's already up here on the graph. The point is 0, 4. So that means when x is 0, it wants the y coordinate, so that would be 4. And lastly, f of negative 3. So I've got to go to negative 3 on my graph on the x-axis and find where it touches the graph right there. So what would that ordered pair be? That would be the ordered pair negative 3, negative 5, right? So that means the function value f of negative 3 is negative 5. All right, so those are function values in the basic order that you would normally get them. Now, if you look at these last 3, it says find where f of x equals 4. So be careful with these. They're a little different than what we just got through doing. So again, look at the notation. What is this number? Well, remember, on the notation, always for functions, what a function value is equal to is always y. So now it's asking you to find the x value when y is 4. So it's the same thing, it's just asking you for the other coordinate, x, instead of asking you for y. They're giving you y. So you got to be a little careful with this because sometimes there is more than one answer. Okay, so let's start with the first one. We want to find any place on this graph where the y value is 4. Well, I knew the y value was 4 up here because we just did that point in part C. But the best way I can tell you to make sure there's not more than one is to look across horizontally and see if there's any other point that touches up at 4, which there's not. So the only x value when y is 4 would be 0. So I'm going to say x equals 0 here, okay, because we're looking for the x values. Now, on function values, you will only ever get one answer, okay, because remember, to be a function, that's one of the key things is that all the x's and y's have to be different. So that's going to be 1. But here you can get more than one answer. Okay, so just be careful with these. So if you look at part F, find where f of x equals 3. Okay, so again, here's one point. Okay, here's where y is 3 at 1. But notice right over here, there's another point where y is equal to 3. And that's the point negative 1, 3. Okay, so I got 2 places on this graph where the y value is 3. That's what that's asking me. Okay, where is f of x equal to 3? Well, that would be at x equals negative 1 and at x equals positive 1. right? So there's 2 places. So again, looking horizontally for these is how you would kind of make sure that you're going to get them all. All right, and then let's look at the last one. Where is f of x equal to 0? Okay, so again, where's the y value equal to 0? Well, here's place, y equals 0. That's the ordered pair 2, 0, and then right here. So those are the only 2 places on this graph that cross where y is 0. So that's at -2 and +2. Now, just so happens on these 2 that it's positive and negative of that same value. That's not always true, okay? So you could get an answer like -2 and 7. So it's not always going to be the positive and negative. Just so happens that's what this graph is showing, but that's not always the case. Okay, so that's not a pattern, so be careful with that. All right, so we're going to do the same thing. This time we're going to be using 2 graphs. So if we look at number 13, this time we have 2 functions. Function A, which is the blue, and function B, which is the red. So again, A of x, that's function notation. Okay, and this letter can be anything. On the last example it was F because that's typical. Function starts with the letter F, so a lot of times they'll start you out with f of x. But you can be given any function, so you just have to remember this is the notation for functions. Okay, so in this one, A of x is the blue graph, B of x is the red graph, so be careful what you're answering when you see these kinds of problems for your homework or on a test. So part A says find A of 2 on A of x. So again, remember, this is the x value, so we're looking for the y value on part A. So we're going to go to function A and find where x is 2. So on function A, where x is 2 is way up there. Okay? So what is that ordered pair? You don't have to write it down. You can just write your answer, but just so you see it, that's the ordered pair 2, 4. So this question is asking you for the y value when x is 2. Okay, so that would be, so I'm just going to write it again, A of 2 would equal 4. Okay? All right. Now, it's asking you to find B of 2 on function B of x. Well, I'm still at 2, but if I go to function B at 2, I'm at this point now, which is the point 2, -1. Okay, so on the blue graph, which is function A, my value for y when x was 2 is 4. But on the red graph, which is function B, I still have an x value of 2, but now my y value is -1. So on this graph, B of 2 would be -1. Okay, so again, these are not really hard, but it is very easy to get them mixed up, write down the wrong answer, so just take your time with them. All right, so we're going to do the same thing on function A and function B for parts C and D at 0. Okay, so 0 is right here. So on the blue graph, function A, that would be the ordered pair 0, 2. Okay, so the y value would be 2. So A of 0 is 2. And on the red graph, function B, here's where x is 0. That's the ordered pair 0, -2. So on B of 0, our y value is -2. Okay? So again, just be careful. All right, the last 3, just like we did up above, now they're giving you the y values. They want you to find the x values. Okay? And again, these may or may not have more than one answer. All right, so go to the function B of x, which is the red graph, and find the y values of 4. Okay, so the red graph, so y is 4 right here. Okay, there's y equals 4. So if we look at the red graph, this is the only point where the y value is 4. That's the ordered pair -4, 4. Okay, again, go horizontally. There's no other graph on the red graph. There is on this one, but not on function B. That's the only place on function B where the y value is 4. So your x value would be -4. All right, now we're going to go to function A of x. That's the blue graph. So where on the blue graph are the y values equal to -4? I'm sorry, equal to +4. Well, again, here's 4. and here's my blue graph. So you can quite easily see there are two places on the blue graph where the y value is 4. We already found this one earlier, 2, 4, and this is the point 4, 4. Okay, so again, this question is saying, find the x values where y equals 4 on function a. So the x values would be at 2 and at positive 4. Those are the two places where y equals 4 on function a. Okay? Alright, lastly, back to function b, that's the red graph. Find where the y values would equal 2. Okay, so again, go to the y equals 2, that's right here. And the only place on the red graph where I can find y equals 2, right there. That is the ordered pair negative 3, 2. Okay, there's no other ordered pair on the red graph that would have a y value of 2, because that means it would be on this line right up here. So the x value would be negative 3, and there's only 1, so that one just has one answer. Okay, so function values, again, you guys need to be able to do it just by given a function, but also can you pull the numbers off of a graph? So that's real important. That means you really understand what this notation is asking. So work on that if that's still kind of confusing to you, but that's what you're looking for when you're given a graph. Okay? All right. This next page is all about telling whether or not your equations or graphs are functions, and then we're going to start looking at how do you find the domain. Okay, so let's go over first off what this test is called to see whether or not you have a function, and that's called the vertical line test. The vertical line test is just a way for you to look at a picture of something and telling me whether or not it is a function. Okay, so it says if a relation can be graphed in the Cartesian plane, it's going to be a function if and only if no vertical line passes through the graph more than once. If even one vertical line intersects the graph of the relation 2 or more times, then the relation fails to be a function. Hopefully you remember that from your algebra classes. So basically what this vertical line test says is that if you pick a vertical line, which is straight up and down, and you pick anywhere on the graph to draw it, it can only cross that graph in one place. Okay? If that's true, then this graph is a function. If it's not true, then it's not a function. Okay? All right, so if I look at this first one, no matter where I draw a vertical line, I could draw it here, it's only going to cross at one point. I could do it over here, it's only going to cross at one point. Okay, it only touches this graph in one place. Even right here, it's only going to touch right there. So no matter where I draw a vertical line, it only touches this graph one time. So that means yes, this is a function. Okay? So we're looking at whether or not these graphs are functions based on this vertical line test. All right. Now before we do this one, let's remember what this means. Okay, when you have a solid closed-in circle, that means you're including that point. But when you have an open circle on a graph, that means you're not including that point. So this is not a point on the graph. The point starts right before the number 2, right there. Okay, so when you do the vertical line test, you're crossing the graph only once. Okay, no matter where I go, I'm only going to cross the graph at one point. And then right here, because this is an open circle, even if I draw a vertical line right here, okay, it's only going to cross this whole entire graph, because this is one graph, it's only going to cross it at one place, or touch it, because that's not part of the graph, that open circle. So this is still going to pass the function, the vertical line test, and be a function, because anywhere else you draw the vertical line, it's still going to cross only once. So this is also a function. So I'm hoping that maybe you're asking me the question, sitting there where you are, what if that was a closed-in circle? Well, if that was a closed-in circle, then this vertical line would touch the graph in 2 places, and it would not be a function. Okay, so that's a big difference whether that's open or closed. All right, and then on part C, hopefully you can easily see that no matter where you draw a vertical line, it's going to cross the graph in two places. So no matter where I pick that vertical line, it's going to fail the vertical line test. And it says I only have to do it only once. Can I find that? I can do it a lot of times here. But if you can find only one place where that happens, this is not a function. Okay? So that's what the vertical line test helps you figure out. Sorry about that, can't write. Is if you have a graph, you can easily tell whether or not it's a function by doing the vertical line test. Okay. Now, if you have an equation, that's different. Okay, we've already talked about how that works, and we'll look at that some more as well. But this is just for graphs. Okay, so that's when you can use that test. All right, so you got a few more things to do, and all of it is about domain and range for your function. So we're going to start with the domain. There's a lot of information on this page, and what I'm going to try to do is give you just quick examples, and then on the next page we'll do the examples that were given to you. So, determining the domain of a function, okay, given an equation, not a graph, but an equation. So it says that the domain of a function is the set of all what values that can be used in an equation. So hopefully, again, you remember from algebra that the domain is the set of all the x values. The range is the set of all the y values, which we'll talk about in just a minute. But right now, we're just looking at the domain, okay? This whole box here is about the domain. All right. Good news is that most of what we do in here, for now, a lot of the domains will be all real numbers. That means you can use any number you want for x and work out your equation. There's a few restrictions on a couple of types of functions. So that's what this page is telling you, and hopefully after you do it for a while, you'll kind of see that there is a pattern. You can kind of see real easily which functions are going to have a problem with the domain. Okay, so first off, polynomial functions. Do you remember what a polynomial function looks like? Okay, this is just an example. A polynomial function would be like 3x to the 4th plus 5x cubed minus 7x plus 8. Okay, polynomials. They're just a bunch of monomial expressions tacked on together. So the domain of any polynomial function is the entire set of real numbers. What that means is no matter what value I give you for x, like I say, figure this out when x is 1. Or you can plug 1 in there and you can give me an answer. So that means 1 is in the domain. If I say plug in negative 99, well, you can put negative 99 in all of there for x and you can get an answer. So negative 99 is in the domain. So what this is telling you is that when you have a polynomial, there is no number that you can't put in here and work it out. Even fractions, even decimals. You know, you could put in 1/4, you can get an answer. You could put in a square root. You could put in a square root of 2, you can get an answer. So the domain for any polynomial is the set of all real numbers. And if you remember how to write the domain that way, okay, you guys, big time, if you don't know how to do interval notation, that was in the prerequisite set that's on Canvas. You need to watch that video and make sure you can write your answers in interval notation, because that's how we do that in here. If you need help, let me know. But there is a video and a little one page of notes to help you remember that if you have forgotten. So how do I write the set of all real numbers in interval notation? That would be from negative infinity to infinity. Okay? This is how we write everything in here, so please make sure this is called interval notation. And again, all of that is on Canvas under your prerequisite skills, things you should know before you come to class. So please make sure you can do that. All right, so polynomials are easy. Always, your domain is all real numbers. You don't really ever have to think about it. All right, now we're going to talk about rational functions. Okay, what's a rational function? So an example of a rational function would be like 6 over x minus 2. Okay? All right, so a rational function is when you kind of have a fraction, but in the denominator you have a variable. Okay, that's what makes it rational. If you just had 6 over 5, that's not a rational function. Rational functions have to have a variable in the denominator. All right, so it tells you that the domain of a rational function consists of all real numbers of x, so all of these, except for those in which the denominator is 0. Okay? It says to find these values excluded from this function, we're going to set the denominator equal to 0 and solve for x. Now you may or may not have to do that because you can do this in your head, but some of them are a little bit harder than others. Okay? So I know that the domain of this function is all real numbers except whatever makes the denominator equal to 0. Okay? So if you can't see it, what it's telling you to do is take the denominator and set it equal to 0. And I'm going to say this is what you're doing to look for exclusions. Okay, the numbers you're going to take out of the domain. So set just the denominator equal to 0 and solve that. So we would add 2 to both sides and we get x equals 2. So x equals 2 is an exclusion. We have to take it out of the domain. So that means the domain for this problem would be all real numbers up to 2, because we got to take 2 out, and then any number bigger than 2. Okay, so that's what that looks like. That is all real numbers except for 2. And remember, in interval notation, that parentheses means you're not including it. Okay? So again, please make sure you know how to do interval notation. All right, an even root function. Even roots. So a square root is an even root. So maybe like the square root of 2x plus 5. That would be an even root. Okay? Or a fourth root would be even root. I'll do the same thing underneath. So this is a square root. We don't put the 2 there. It's understood to be there for square roots. Fourth root, so that's what it means by even root. Sixth root. So it says the domain of an even root radical is any x value for which the radicand, that's the part under the radical sign, is not negative. So that means this has to be positive. So in order to do that, it says set what is under the radicand greater than or equal to 0 and solve it. So take what is under the radicand, set it greater than or equal to 0 and solve it. So I'm going to get 2x is greater than or equal to negative 5 when you move the 5 over, and then divide by 2. So x has to be greater than or equal to negative 5/2 in order for this function to be positive. Because remember, you can't take the square root of a negative number. So that's the boundary. So anything bigger than negative 5/2, which is negative 2.5, will work. So how do you write that in interval notation? Okay, so since it says greater than or equal to, we're going to use a bracket, because that means we're going to include negative 5/2. And everything bigger than that means it's going to go to positive infinity. Okay? So brackets means you're including, parentheses you're not including, and then always remember, anytime you're using infinity, you always use a parentheses, because it keeps on going forever, so we can't close it in. Okay? All right, and then lastly are odd root radicals. So the way we began with all real numbers is the way we're going to end. So on an odd root radical, the domain is always all real numbers as well. So an example of odd roots would be the cube root of something. Let's say the cube root of 5x minus 1. Or another odd root would be the fifth root of that, right? So as long as the root is odd, your domain is all real numbers. So let me just quickly explain why. So remember, with even roots, you can't take an even root of a negative number. So that's why you have to figure out the boundary. Where do you start in order to get positive answers? But on odd roots, you can take a positive or negative root of something odd. So that means there's no problems with those, okay? So we're going to do a few more of these on the next page in just a minute. So real quick at the bottom, there's a little asterisk here. It says there are only certain functions where the domain would not be all real numbers. In this course, rational functions like these, okay, even root functions like these, and then logarithmic functions, okay? So really, out of all the functions you get when you're asked to find the domain, everything will be all real numbers except for rational functions and even root numbers currently. Then when we get into logarithms at the end of this semester, we'll add those as well, okay? All right, so that's nice to know, but for now, that's what we're doing. And then, again, watch the video if you need help on interval notation. All right, so last page, let's work on finding the domain. And then the last 3 problems on this page, we're going to find the domain and the range of an actual graph instead of a function. All right, so state whether each of the following is a polynomial, a rational function, or a root function, and then state the domain. Okay? So let's go through and do the first sentence first. So let's look at each of these and decide whether they're polynomials, rational, or root. So number 15, that's just polynomial. Okay? That's when you just have a bunch of monomials tacked on together. Number 16, when you have a variable in the denominator, that's a rational function. Obviously, when you see a root sign, you know that's a root, and this is a square root, so not only is it a root, I'm going to say it's an even root, because they're different if they're even or odd. Okay, this has a root, square root, so that's an even root function. Okay. This is a root, but it's a 3, so this is an odd root. And lastly, we got a variable in the denominator, it's a fraction, so this is another rational. So in this set, we have 1 polynomial function, we have 2 rational functions, and 2 even roots and an odd root. So remember what we just did on the last page. If I am giving you the domain of any polynomial function, it is all real numbers. I can use any number in here and I can get an answer. Same thing with odd roots. If you have an odd radical, then the domain is all real numbers. So I'm just trying to kind of put together what we just did on that last page. Okay, so this was the first type, this was the last one. So those are the easy kind of domains. I don't really have to think too much about it. What that means is any number for x, I can put in here and I will get an answer. Okay? These other ones, I can use almost every number, except there's some exclusions or a boundary. So for a rational function, remember we need to look for the exclusions. Okay, so I'll write that down. So how do we find the exclusions? We set what's in the denominator equal to 0. And you solve that. So move that -1 over the equal sign, it becomes positive. So that's your exclusion. Okay, so your domain is all real numbers except for 1. Okay, well, how do you write that? All real numbers except for 1 would start at -infinity and stop at 1, because I got to take 1 out, and then I would start again right after 1 and go to positive infinity. Okay, it's an infinity sign right there. Oh, I'm just making it worse. 1 to infinity. There we go. Okay. All right. So there's your domain. So that is all real numbers except for 1. All right. Even roots. Even roots, we need the boundary. So we take what's under the radical and set it greater than or equal to 0. Okay. So we're going to solve that. We're going to move the 2 over. It becomes positive. And then divide by 5. So we get anything greater than or equal to 2/5. So how do you write that as an interval? That would be from 2/5, including it, to infinity. Okay? And that's a parentheses. Always use parentheses with infinity. Okay, you've got another even root. So this is nice because even if there's extra stuff here, remember the way to find the boundary for an even root radical is only to set what's under the radical greater than or equal to 0. Okay, this does not really matter. I can put anything in there. This is the problem. So no matter what else you have in a root problem, you just take what's under the radical, and that's what you're looking for. All right, now I picked this problem because of this minus sign. You got to be real careful with those. Okay, so typically you want x to be positive. So I'm going to take that minus x, move it over to the other side, and it's going to become positive. Okay, but the problem some students have with that is you read this backwards, and so you end up not doing the right direction with this sign. So if I ask you to read this the way it is, you would say 7 is greater than or equal to x. So if you read it backwards, it would be x is less than or equal to 7, right? The open side is pointed towards the 7. So I'm going to just rewrite it just so you can see this, because this is a very common mistake. X is less than or equal to 7. So I want you to see that these are the same, right? Look at the opening. The bigger part of that inequality is facing the 7. So when you read this out loud to yourself, 7 is greater than or equal to x, that's the same thing as x is less than or equal to 7. So when you're doing your intervals, you got to be careful because this means all the numbers less than 7. So this is deceiving because a lot of you will say, but it's a greater than sign, why isn't it numbers greater than 7? Okay, because this says 7 is greater than x. And if 7 is greater than x, that means x has to be less than 7. So just be careful when you write those out on your paper. So what are numbers less than or equal to 7? Okay, less than or equal to 7 are numbers like 6, 5, 4, 3, 2, 1, right, and all the negative numbers. So this means numbers less than 7 would start at negative infinity and then go to 7, and then that's where you would stop. Okay, these are numbers less than 7. Okay, so that's your domain. All right, we already did this one. So now we're back to rational functions. So on rational functions, remember we got to look for the exclusions. We're just taking certain numbers out. Okay. All right, so how do we look for the exclusions? We take the denominator, x squared minus x minus 6, set it equal to 0, and solve that. Okay. All right, well, how do I solve this? If you remember, and if not, we're going to get to it eventually, but you got to factor. Okay, so the way that I factor a trinomial is into two binomials. So I know that the first two numbers, x times x, has to give me x squared. I know the last two numbers have to give me 6, and I need a negative 1 in the middle. So that means I'm going to do a negative 3 and a positive 2. Okay? So if I FOIL that out, I get that. So hopefully you guys got to remember how to factor. And then once you have your factors, you set each factor equal to 0 to get your numbers that you're going to exclude. So if you set x minus 3 equal to 0 and move the 3 over, you get positive 3. If you set x plus 2 equal to 0, you'll get x equals negative 2. So remember, these are the exclusions. So I got to take 3 and negative 2 out of this. Now this one I'm going to do a little graph just to show you. Sometimes this helps. So x can't be negative 2 and x can't be 3. And I got to put them in order on the number line because interval notation. So every other number between negative 2 and 3, left of negative 2, and to the right of 3, all of those work. The only exclusions that are not in this answer are negative 2 and 3. This might help you do your interval notation because you have to do interval notation from left to right. Remember, this is negative infinity over here, and that's positive infinity. So write this using intervals. So you do this interval first, negative infinity to negative 2. Okay. Then you would say union, because you got more than one. So everything between negative 2 and 3. and then union, and everything bigger than 3. Okay, so that's the domain. Okay, written in interval notation. So I had 2 exclusions, 3 and -2. I took them out of all real numbers. So that's what it looks like. Okay, so that domain right there says every number works except for -2 and 3. So that's how you would write it. All right, lastly, looking at a picture, how can you find the domain and range? All right, so we've just done the domain a bunch of times. So that is what x values are you using, and then the range would be what y values are you using. Okay, so we got to pay close attention to open circles, closed circles, and circles and arrows. Okay, so be very careful when you're doing these on your own. All right, so the domain is from x to x. What's the lowest x and the highest x that I use? Well, this graph stops at -2, 2, so the lowest x, smallest x value is -2, but I'm not including it, so that would be a parentheses. And the largest x value I'm using is a +4, which is a closed circle, which means I am using it. So the domain of this graph, the x values, okay, from what x to what x, that would be -2 to 4. So when you're doing the range, you're looking at the y values. So smallest at y would be down here, largest y right here. All right, so here's a point on your graph, which is -1, 0, looks like. And then the highest point on your graph is at 2, 6. So here's 6 up here. So your y values run from 0, y value, up to 6. Okay, and you're using that and you're using that. Those are both points on your graph. So the range would go from 0 to 6. So remember, these are the y values, these are the x values. Okay? So you gotta be careful with those, just again because of those circles, open circles, closed circles. All right, so let's look at 22. What's the smallest x value? Looks like right here at -4, but you're not using it because it's open. And then the largest x value would be here at 5, but you're never going to get to 5 because this is an asymptote. That means you're not using it, those dotted lines. So this arrow is going to keep going, but it's never going to touch 5. So you're not including 5 either. So that would be a parentheses over here at 5. So we got a parentheses over here at -4, and we would use a parentheses over here at 5 because it's never going to touch. Remember again, dotted lines on a graph, that's what we call an asymptote, which means you can't use that number. So if you can't use 5, you got to use a parentheses. And then there's nothing over here to the right. So that's the end of the domain. Your range are your y values. So find the smallest or lowest y value. That would be at -3, right? That's the smallest. This one doesn't seem to hit it. So -3 is the smallest. Now what's the highest y value? Well, this arrow says it's going to keep going forever and ever and ever. That's what an arrow does. So your largest y value is not 5, it's not 6, it's not 7, it's not 8. It's going to keep going up. And when I go all the way up and never stop, that's a positive infinity. Okay. All right. Here's a circle. So all of these points are on the graph. So I just need to kind of, I know it's very small, but let's kind of figure out what my x values are. So here's the end of the circle right there. So that looks like -1 for the x. All right, that's the smallest x value. And then the largest x value looks like it's at 7. And those are points, so that's going to be a bracket. So we're going to go from -1 to 7 for the domain. And then you're going to do the same thing for the y values. What's the smallest y value? Looks like -9. And then the largest y value looks like -1. So the only y's you're using are between -9 and -1. Please remember when you do interval notation, smallest number, bigger number. You can't write 7, -1. That would not make any sense. Okay, you'd get it wrong. So you always have to use the smaller number than the bigger. And when you're doing several intervals, they too must be in order. So I always remind you guys that intervals have to be written in numbers from left to right, okay? So again, please practice that if you guys are a little bit rusty on interval notation, because that's very important in this course. We're going to use it a lot, okay? All right, so that ends 3-1. I got a little long-winded there, but a lot of this stuff is real important to you as far as kind of being successful for the rest of the course. So I wanted to spend a little bit of time on it. So you should have enough now to get to work on your homework. And if you need any help, as always, please make sure you email me or go to one of the tutoring options that you have for the course. We are all here to help you and make sure that you succeed, okay? All right. See you back here next time.